This module will show some examples of how infrared radiances are used to estimate sea surface temperature or land temperature. As we recall from previous modules, brightness temperature is not the actual temperature of an object. The brightness temperature in a cloud-free environment is not the surface temperature because 1. The atmosphere above may absorb small amounts of radiation emitted by the surface, even in atmospheric windows that are not perfectly transparent, or 2. The surface is not a black body. The brightness temperature is calculated as a function of satellite observed radiance. The goal for estimating SST is to calculate a brightness temperature given an observed radiance and correcting that brightness temperature using radiances in multiple bands to correct for water vapor absorption. Of course, in cloud-free areas, surface emissions are not clearly observed, and we can't do this. In Schwarzschild's equation, shown in this form, we seek to estimate SST using radiances in bands in which the first term on the right-hand side of the displayed equation dominates the second term in magnitude. This means that the direct transmittance, tau, needs to be large, or that the weighting function needs to have as large a value as possible at the surface. This occurs, or most closely occurs, in atmospheric window channels, such as those highlighted. The plot shows direct transmissivity of the atmosphere as a function of wavelength and the contribution of each of several atmospheric constituents to total extinction of radiation along a vertical path through that atmosphere. As you know by now, total extinction is limited at shortwave infrared wavelengths around 4 microns and between 8 and 12 microns, with the exception of the ozone band. Even within the IR atmospheric window, different bands experience slightly different sensitivity to water vapor, as we discussed during the modules discussing GOES, and the small differences in brightness temperature in such bands can help quantify the column integrated water vapor present. For example, AVHRR, the visible and IR satellite sensor on NOAA 19, uses a shortwave infrared channel and 2 terrestrial IR channels to estimate SST. Differences between AVHRR channels 4 and 5, the red and blue shading, will occur because of variations in column water vapor because other molecules have negligible effect on absorption at 10 to 12 microns. The GOES channels used to compute SST are highlighted here. 3 in the terrestrial atmospheric window, a shortwave IR band, and 1 on the shoulder of the water vapor absorption band. And JPSS satellites have their own bands that are used for SST, as we covered before as well. Let's think about what an increase in water vapor then does to the brightness temperature. Suppose we have a homogeneous single layer atmosphere, shown in light blue, with direct transmissivity of 90% and some temperature, and a blackbody surface with a higher temperature. We can simplify the integral of our Schwarzschild's equation since T is constant with height. By plugging in 0.9 for tau, then the top of the atmosphere radiance is simply a weighted average of surface emissions and a small amount from the atmosphere. Therefore, the brightness temperature is not exactly the surface temperature, but in this example is instead slightly lower. Observing this simple atmosphere with 2 channels allows us to incorporate the derived water vapor path length into a corrected temperature that more closely resembles the true blackbody emission temperature of the surface. As we'll see here, higher concentrations of water vapor increase the difference in brightness temperatures between bands that have slightly different sensitivities to water vapor absorption. Suppose that the same atmosphere has a transmissivity of 95% to 11 micron radiation, but only 90% to 12 micron radiation, which are approximately the center wavelengths of AVHRR channels 4 and 5. We can solve for the optical depths of the atmosphere at each wavelength using the relationship between transmissivity and optical depth, tau equals e to the minus delta over mu. In this case, we'll neglect the mu. In this example, we get vertical path optical thicknesses of about 0.051 and 0.105 for the 2 channels. The difference in radiances, therefore, is about 5% of the difference between the brightness temperatures. However, if we double water vapor concentration and carry out the same calculations, we find that the difference in radiances between the two bands only goes up to 9% of the difference between the brightness temperatures, even though the optical depth is doubled. And this is because of this exponential relationship between transmissivity and optical depth. So the point here is that water vapor path in the atmosphere does not correspond linearly with changes to split window differences between neighboring infrared bands. Ultimately, we require somewhat complicated empirically derived relationships to estimate SST based on brightness temperature. The AV-HRR multi-channel sea surface temperature estimate derives surface temperature as a linear combination of each channel's brightness temperature, and SST therefore takes on some linear form such that SST equals a constant, plus unknown coefficients like the B and C here, times brightness temperature for various bands. The coefficients are empirically derived by comparing known observations of SST, such as through ship or buoy data, to satellite brightness temperatures. At night, we can also use an additional channel or channels in the shortwave infrared, but we cannot do so during the day because of the additional reflected solar radiation that would contaminate our estimate. The following shows some different versions of the multi-channel SST relationships used without the coefficients filled in. Note that the nighttime relationships incorporate 3 bands, one of which is the shortwave IR, channel 3 in this example. All relationships include a term that corrects for off-nadir observations along increased path lengths that increase the amount of absorption that occurs. Different satellites, GOES or the JPSS satellites, use similar relationships but have different coefficients given the available bands on each platform and satellite characteristics. Consider that we are only detecting information about the very top of the ocean surface. Liquid water scatters infrared radiation efficiently, therefore emissions by water molecules below the upper 1 millimeter, shown here above this dashed line, are absorbed before they escape the water. Therefore, SST estimates made with infrared are skin temperature estimates, capturing the temperature of just the thin layer at the top. Microwave-derived brightness temperatures, which we haven't looked at yet, represent SST over a slightly deeper layer because the microwaves are not as susceptible to scattering by liquid water. But down here, anything that's emitted gets absorbed or scattered quite quickly. A sea surface temperature product can then be produced that covers much of the globe. This example is derived from multiple sources, including buoy data. But we'll see in the lab that satellite brightness temperatures can be reliably converted to SST with some limitations. In this plot, the warmest sea surface temperatures are found over the tropical whirlpool over the West Pacific. Brightness temperatures above or in clear air here would therefore be quite warm, although large differences in atmospheric window channels might exist because column water vapor is often high. The SST data can also be used to produce products such as the weekly SST anomaly seen here. This example shows a prominent SST positive anomaly in the North Pacific near the Gulf of Alaska and perhaps a weak La Nina temperature distribution in the eastern equatorial Pacific. Similar procedures can be used to estimate land surface temperature or moisture. We won't explore these in detail in this module, but we will briefly consider that objects over land are diverse, much more so than over the ocean, and many of these objects are not even close to approximate blackbodies. An example of emissivity for a few various surfaces is shown at bottom, with the direct transmittance of the atmosphere shown at top. Some of the surfaces plotted are close to perfect emitters in the IR, such as smooth ice or salty soil. However, some of the surfaces are not. For example, seawater, although a good emitter in the atmospheric window generally, is actually not a good emitter at around 4 microns. Sandy soil cannot be approximated as a black body between roughly 3 and 5 microns or 8 to 11 microns. This means that brightness temperatures over such surfaces at the wavelengths listed will be low. Not necessarily because the atmosphere is opaque, but because the emissivity, and therefore the first term on the right-hand side of the Schwarzschild's equation, shown earlier in this module, is small relative to what it would be if we assumed epsilon equals 1. For the most part, vegetation is an efficient emitter at IR wavelengths. Although dry grass is shown here, as well as eucalyptus, to have emissivity of only 90% between 4 and 5.5 microns. Man-made surfaces also have variable emissivity. Asphalt, concrete, and steel are examples of objects with high emissivity at a variety of IR wavelengths. However, aluminum and brass are extremely poor emitters, as seen by the orange and pink lines at the bottom. Even if hot, the emitted radiance, and thus the brightness temperatures representing these surfaces, would be quite low.